Hey, just a update video here. I've been working on this project off and on for I don't know, a few months maybe. So this is an old concept, an analog version of the cell matrix called the Songline processor, and I built a box to emulate this in hardware many years ago, and it was 2010 technology that I used, and so I've upgraded with a Raspberry Pi 4 as a workhorse and an interface board up here, and this is going to basically be a really cool vintage wooden box with all these knobs and dials on top, and that cool old style skeleton key power switch that I did in another video. And so I just got this board soldered up yesterday, and thought I'd do a quick status update if anybody is keeping score at home, or even if not. So this whole thing is just USB-C powered, and a few interesting developments. So first of all, got the board soldered up for the most part. So there's about 20 op amps on here for conditioning signals. There's some trimmers for setting some reference voltages, 1 volt, 2 volt, etc. A few random logic chips. These 4 chips with the small legs are D to A converters. So there's 8 channels of D to A output, which you can read here. And then this chip right here is an A to D, and it takes 4 analog input channels, converts them to digital, which can be read by the processor. Well, the first issue that I ran into was this business of wiring problems. So I designed the circuit, I built it on a proto board, I tested it, it seemed to work pretty well. I went ahead and made this printed circuit board and sent that off to be manufactured. And then as soon as I hit the enter key on that, I took a closer look at the design and realized I had a problem in my design. So the analog to digital conversion would sometimes hang up, and I finally figured out why. And so small engineering change in this flip-flop that I have down here. Instead of having pin 2 grounded, I needed pin 2 connected to pin 6. That's a 7474 if you want to look it up. So here's what I did when I got the boards back. I took one of the boards, I cut the traces for pin 2. This is a line that connects to ground. This other end goes out to ground. And I cut those, right? And that will isolate this pin from ground. And then what I did was I did a little engineering change on the fly. So basically just added a jumper wire between pins 2 and 6. I did not think I could do soldering at this scale because my skills aren't that dialed in, but it seems to work. So I've got my jumper in there. So that was one little detail that I had to take care of. The next detail, when I was soldering it, I got down to my last chip, which is the A to D converter, and you can see the footprint for it right here. And the problem is, this is the actual A to D chip, and so I ordered the wrong part. Right, this was the one that I used when I was testing it on a proto board, but I really need a TSSOP, a thin outline package. So ordered that, and fortunately, I placed my order Friday afternoon. DigiKey has already shipped it, and it should be here on Tuesday. So yay for DigiKey. But meanwhile, I wanted to explore the behavior of this. So the D to A system should be working, right? So I can take my multimeter, I can put this on volts, and I can hook up one lead to ground, and any ground source on here will do. So I'll just plug this into the Ethernet port. And what I should be able to do is from software drive these 8 output pins. So the left of each of these pair is the positive analog output. And right now, they're just kind of whatever values, 90, 0, 224, and so on. These are millivolts that we're reading. And the right sides are all ground, so those should be 0. So so what do? You write a little bit of software, and So let's SSH into our box. I'm trying to type amongst a flurry of wires. So here's the basic setup for the digital to analog conversion. So there's 8 bits of data, and I only use 7 of them to output, because my input is 7-bit. So I can write a data value out. I have 3 select bits, which will select one of the 8 output channels, and then I have a write signal. When you bring that load, that begins the conversion. And so really simple test program here, right? I'll just read in a channel number and a value, and the values go from 0 to 127. CSE 224 students, don't do what I did. I did not check the return value from scanf. I have no way of knowing if I made a typo. I'm willing to live dangerously. Anyway, we take the value, we write that out with a write byte command that sends it to wiring pi pins 0 through 7. That's hardwired in the wiring pi library. And then we write the 3 channel select lines based on the 3 least significant bits of channel, and then we drive the write signal low. And that should send a signal out. So we can go ahead and run this. So it's asking me for a channel number and a voltage value. So right now this pin over here is reading about a 0. So let's say channel 0. Let's write a 64, and you can see that comes up to just about half a volt. So 127 is full voltage. So if I do 0 and 127, that brings me up to just about 1 volt. And I can take channel 6 and I can drive that to 96, which should be about 3/4 of a volt, 750 millivolts. So channel 0 is still intact. And if I go over here to channel 6, there's our 3/4 of a millivolt. And channel 7 has got something nominal right now. I can drive that down to a 0. So there's our close to 0 volt signal coming out of channel 0, and so on. So so this is working. This is good progress. So the digital to analog piece of this is running fine. And I'll get this chip on Tuesday, and sometime after that, solder it up and see if I can get the whole two-way communication, A to D and D to A, to run. The other thing that I did was figured out, meaning I looked on Google, right, how to get a GPIO pin to tell me when the system is shut down. So right now I have wiring pi pin 31 set to deliver 3.3 volts when the system is up. And if I shut the system down, so we'll sit here at wiring pi 31, shut the system down, and when the system finally goes down, the voltage drops to 0, and I can use that with the locking system to dial in some nice momentary action. So that's the basic setup, and let me just kind of show you the rest of the system. So there's a series of knobs and meters and plugs that people can use, and so on and so forth. And so each of these is tied to a little connector, and these connectors will just slide into 4 rotary knob inputs, 4 general analog inputs, and 8 general analog outputs. These go to phono plugs, 1/8 inch, that you can use to send signals in and out. These are the voltage trimmers that I use to divide signals down, because everything is 2 volts inside but 1 volt outside. And then all of this will go inside this nice case, which is this really beautiful wooden box that I can't do justice with on the document camera, but it's, you know, got a nice lock here in the front, and open it up. And so my fiance gave this to me last year, and you know, it's got this nice fabric inside, and you know, the obligatory brass hinges that you need for any kind of cool project and so on. And so you know, the electronics will sit inside here, and everything will be attached inside, and the faceplate that's going to go in here is a piece of plexiglass, and this will go a little bit below the surface. And then that locking mechanism that we saw in another video, that will go right here with the faceplate. And then everything else is just, you know, dialed in. So the main meter will go here, and then these knobs and such, 3 of them are just general potentiometers, so they'll go under here. And I've got the little, you know, matching hole that will snap into, so that when you turn it, this thing won't, you know, turn like that. So it'll hold it in position. And so those will be the knobs. And we have face plates, and we'll have knobs that go on top. So that's all taken care of. And then there's a nice multi-turn potentiometer, which will go right here. That's the higher precision one. So it's 10 turns to go from 0 to full resistance. So that lets you put in more precision. And then there's a select knob, which will go right here, and we'll let you choose any of these 4 analog inputs, these 8 analog outputs, to send to the meter. So if you want to monitor what's going on while the system is running, you can do that. And then finally, power will come in right over here. There's an adapter I printed, and this will be, you know, your USB-C connection. And so you just plug that in there, and power will come in. And I've cut into the USB cable, so I have, you know, the source and the destination. And this will go into a little circuit board with a relay that monitors that skeleton key, and is used to turn the system on when you turn the key one way, and when you turn the key the other way, instead of just cutting the power, it will drive a signal low that the Pi will pick up, used to initiate a shutdown. And then when the shutdown is complete, that pin 31 will go low, and that will release the relay, and the whole system will power down. So that's the theory. That's what I've been doing, and we'll see how this goes. But new parts coming in on Tuesday, and I'm just kind of working at my leisure building this up. A lot of fun dremeling, you know, these things, and these don't have to be precise, because, you know, they get covered by something larger. These get covered by that dial and so on. And so the approximate mock-up looks something like this. And then you know, this was done in Inkscape, so that let me place my components and let me make a template that I used for actually drilling these. But then in Inkscape, I can remove everything except the labels, and then print those out on adhesive-backed stickers. So I have some 8.5 by 11 sticker sheets that'll go in a laser printer, and I've got some that are white and some that are clear. So I can print on that, and then just cut out the labels and put them onto here underneath the actual hardware. And there we go. We should have a pretty cool looking Songline processor in this great old wooden box. All right. I don't know how much any of this means to anybody, but I thought I'd document it anyway. So thanks for watching. Take care. Bye.